Good morning and good afternoon, everyone. We are Hadi and Marwan Abudif, and today we're presenting the final milestone 2 delivery for Pixel Perfect, our content-aware super resolution system for retro game assets. Since our last update, we have fully scaled our model to train on the entire dataset, enabled adversarial training for sharper textures, and introduced a new palette constraint loss to strictly enforce retro color palettes. Retro games like NES and SNES run at extremely low resolutions, around 256 by 240 pixels. When you display these on a modern 4K monitor, they need to be upscaled massively. Standard methods like bicubic interpolation just produce blurry, muddy results. And here's the interesting part. Even the state-of-the-art super resolution models fail on pixel art. They're trained on photos, so they interpret those sharp pixel edges as noise and smooth them out. You get this oil painting effect that completely destroys the artistic intent. What we need instead is a model that respects pixel art geometry. For our dataset, we selected the Kaggle pixel art dataset. It contains about 89,000 pixel art images of sprites and game objects, all at 16 by 16 resolution. We split this 80-10-10 for training, validation, and testing. The dataset is around 500 megabytes, which is well within the capacity. A very important part of our pre-processing is the nearest neighbor downsampling. We resize the sprites to 128 by 128 using NN interpolation to create our high-res targets. Then downsample to 32 by 32 using NN to create the low-res inputs. This preserves the blocky geometry that defines pixel art, unlike bicubic, which introduces blur. Here you can see actual samples from our pre-processing pipeline. The left column shows the raw high-resolution sprites, the middle shows them downsampled to 8 by 8 using nearest neighbor, and the right shows the processed low-resolution inputs that get fed into the model. Notice how the NN downsampled versions maintain hard pixel boundaries. There is no smoothing or blending between colors. This is the key insight. By training with NN downsampled pairs, we teach the model that the relationship between low-res and high-res is geometric and blocky, not smooth and continuous. Our model is based on SGRAN. The generator uses the RRDBNet architecture, and the flow is a 32 by 32 low-res image enters the network, passes through an initial convolution, then through 8 blocks. We reduced from the standard 23 because the pixel art geometry is much simpler than photorealistic images. Then the features are upsampled twice using nearest neighbor interpolation, giving us our 128 by 128 output. Two important design choices we went for: no batch normalization in the generator to prevent artifacts, and residual scaling of 0.2 for stable training. Each block contains 3 residual dense blocks, each with 5 convolutional layers densely connected. The discriminator is a standard VGG style classifier with batch norm that progressively downsamples from 128 down to 4 and outputs a real fake prediction. Our proposed updates: our first core update remains the nearest neighbor downsampling strategy, which teaches the model that LR to HR mapping is geometric. For milestone 2, we have expanded our second update alongside our Sobel-based edge-aware sharpness loss, which eliminates the oily look of standard models. We've implemented a new palette constraint. This loss penalizes generated colors that do not fall perfectly onto a discrete 8-bit or 16-bit color grid. This entirely prevents color drifting, a common issue where GANs invent new colors not present in the original sprite's limited palette. Our total loss now combines L1 pixel loss, LPIPs, perceptual loss, our edge loss, and a new palette loss. And we have successfully enabled adversarial loss to push texture sharpness to the maximum. For this final milestone, we scaled to the full dataset and trained for 20 epochs with mixed precision AMP on a Collab T4 GPU. Looking at the chart, the discriminator loss completely collapses towards 0 by epoch 14, meaning the generator has learned to produce outputs that perfectly fool the discriminator. Exactly what we want for pixel art, where the output should be indistinguishable from the real sprites. The adversarial loss component dominates the total loss generator, driving texture sharpness, while our edge-aware and palette loss remain low and stable, proving our custom constraint guide the GAN without destabilizing training. This full-scale training is the core achievement of milestone 2.
Okay, so good morning everyone. My name is Hadi Hisham. Okay, and then we're going to start from slide 8. Okay, so here's a side-by-side comparison. The left column shows the ground truth at 128 by 128. The middle shows the bicubic upscale, our baseline, and the right shows our pixel perfect model's output. Notice how the bicubic baseline produces harsh, blocky artifacts with exaggerated white edges that don't exist in the original. Our model, on the other hand, produces output that's visually near identical to the ground truth. It faithfully recovers the color transitions and sprite shapes. and bright shades. Okay, so now for our ablation study. To validate the impact of our edge-aware loss, we ran an ablation study comparing three configurations: bicubic upscale, Ether without edge loss, and Ether with edge loss. The number tells a clear story. Bicubic gets a PSNR of only 23.18 and a triple L pips of 0.48. Our ESR GAN without edge loss jumps to 41.51 PSNR with 0.004 L pips, and with the edge loss added, L pips improves further to 0.0029, a 27% improvement in perceptual quality. There is a slight PSNR trade-off, 41.51 versus 41.10, but this is expected. The edge loss encourages sharper outputs which can differ by a pixel or two from ground truth, slightly lowering PSNR while improving perceived quality. This is exactly what LPIPS captures. We want to highlight why LPIPS is the most important metric for this task. PSNR actually favor blurry images because it penalizes any pixel deviation equally. LPIPS on the other hand uses a learned perceptual model to measure how similar two images look to human eyes. The gap is dramatic. Our baseline bicubic has an LPIPS of 0.4874. Our pixel perfect model achieves 0.0062. That's a 79 times improvement in perceptual quality. Essentially, our model's output is perceptually indistinguishable from the ground truth. Okay, now for the SOTA comparison. For context, we compare against state-of-the-art results on Manga 109, which serves as the closest proxy benchmark. It has sharp line art and clean boundaries. The best SOTA model, SWIN-IR trained on DF2K, achieves 32.03 dp PSNR and 0.926 SSIM on Manga 109. Our model achieves 41.1 dp and 0.992 SSIM on our pixel art test set. Now, we want to be transparent. This is not a direct comparison. Different datasets, different degradation models. Our high numbers come from the fact that we're specialized for pixel art with NN with neural network degradation, which is inherently more structured than photorealistic SR. The key takeaway is domain-specific adaptation significantly outperforms domain general models. Now for our team contribution, I was responsible for the data side, downloading and cleaning the dataset, building the neural network downsampling pipeline, implementing data loaders, and creating the dataset visualizations you saw earlier. Marwan handles the model and training, setting up the ASRGAN pipeline in PyTorch, implementing the edge-aware sharpness loss, configuring the training loop with mixed precision and checkpointing, and running the ablation experiments. We jointly worked on evaluation, implementing the PSNR, SSIM, and LPIPS metrics, generating the comparison grids, plotting the training curves, and analyzing the results. Okay, now for our conclusion and future work. To summarize our final delivery, domain-specific adaptation combined with massive data scaling completely solves the pixel art super resolution problem. By integrating neural network downsampling, edge-aware loss, palette constraints, and adversarial training on 89,000 images, we achieved a near-perfect reconstruction that dramatically outperforms generic SOTA models like SWIN-IR. Regarding our timeline until final delivery, the model training and application studies are fully complete. This week we will finish recording this presentation video and clean up the code base for final submission. For future work post-delivery, we are looking at direct 4K upscaling and deploying the model as a lightweight browser extension for web-based retro game emulators. Thank you. This was Marwan and Hadi.